One of the larger problems we have when dealing with our distributions is knowing what the population parameters are. When we looked at a normal distribution, I gave you the mean and the standard deviation. For example, we were dealing with liquid soap bottles in one of the examples on Wednesday, and I said that the mean was 600 milliliters and the standard deviation was 5 mils, and I knew that in advance. On page 273, I have the scores of a huge number of people who took the GMAT exam, the Graduate Management Aptitude Test. Now, I'm going to assume that if you give this test, you can tell what the entire population is doing. And they've given me from this information an average and a standard deviation. Page 273. I'm just going to write down those two pieces of information. My GMAT data has an average of 520.78. And a standard deviation of 86.8. But I do not work for the educational testing services. I do not get to see all of the data from the GMAT exam. So what do? If I want to know, hey, how did the people do on the GMAT exam this year? I take a sample. And I'm just going to pull a number out of the air, and I'm going to say we're going to take a sample of 5. I can figure out what the average of my 5 is. And depending on how I did this sample, I might have to question whether or not I have an average that's close to the true average of the population. Now, here's where we're using the different symbols. X bar is my sample average. Mu is my population average. S is my sample standard deviation. Sigma is my population standard deviation. If I do this once and only once, I don't get necessarily a very good picture. So rather than just doing one sample, let's do a bunch of samples. So rather than just looking at one group of 5 people, I look at, 40 or 50 groups of 5 people. Maybe I look at 8. Maybe I look at 30. Maybe I look at 50. But let's consider page 274. What happens if I do this 8 times? If I do this 8 times, I'm going to get a total of 40 numbers. But rather than treat them as 40 separate numbers, I'm going to look at the 8 averages that I get. Please notice, each row of this upper picture is a set of 5 dots. And then I put a little triangle where the average of those 5 numbers are. So even though the individual scores vary pretty widely, when I look at the averages cluster up a little bit more, don't they? And they cluster around the overall true average for the population. My sample averages, when treated as a group, are a random variable. In and of themselves. So I can, instead of just looking at all of these scores separately, by looking at them as groups and looking at the averages from those groups, I can get a new random variable. Rather than just looking at the GMAT scores themselves. I look at samples. The sample means are clustered up around the population mean. If I were to do larger samples rather than just 5 people, maybe do 10 or 15, or if I were to do more sample sets, then I would get a cluster closer to the population mean. Tia, talk to me. I know my handwriting sucks. Talk to me. Clustered near. Yep. Near. So if I have more samples or larger samples, my sample means get even closer to my population mean. And really, if I were to take everybody, well, that would be the whole population. Then I'd get exactly the population. But I don't know how many people take the GMAT every year. How many people are trying to go to MBA schools in the country? A lot. I don't want to try and average all of that unless I gave the exam and already have all that data. So my sample mean is now behaving like a random variable. If I have a random variable, I automatically get something else. What? This is all of what we talked about in chapter 6 and 7. Whenever I have a random variable, I get a probability that goes, I get a function, I get a PDF. So now here's the question. What PDF do I get from sampling? And now that I have that new PDF, how can I use this number, the sample mean, and what I know about this PDF to figure out population mean, which I don't know all the time. This is going to be based on 4 primary factors. When I take a sample, I may get a group of 5 very high scores off the GMAT exam. I may get a group of 5 very low scores. I might get 2 really low, 2 really high, 1 in the middle. I have no idea, right? the samples themselves will vary. And I have no control over that. If my samples are random or systematic or stratified, remember we talked about all those different ways to do samplings. If I've got a good sample, it's going to vary from group to group. So this is a not controllable idea. I cannot account for variation in my sample. I just have to know what's going to be in there. Similarly, there may be variations in the population. And this is also not controllable, because maybe a lot of people studied really, really hard for the GMAT this year, and last year people were a little more lackadaisical about it. I distinctly remember in the spring of 2020 that the AP exams were really, really different than they'd been the year before, because everybody from high school was stuck at home with COVID. And nobody could come in and take the sit-down 3-hour AP calculus exam or the AP statistics exam. They did the entire thing online, and they had to learn how to do that in exactly 3 months. Scores were a lot different that year. A lot of variation in the population we had no control over. On the other hand, I could say, well, I can control the sample size. Because as I said earlier, if I take a larger sample, or if I take more sample, then I'll get a better answer. That's a controllable thing. It could be expensive to take larger and larger samples, and therefore it might not be worth it. But that's going to depend on the next piece. How close is close enough? How confident are you in the answer you get? And this is also controllable. We can do things as we take our samples, as we make our computations, to figure out these last two. What would be a good sample size for the type of answer we're trying to get, and how accurate, how close do I really have to be? Those depend on the situation. But I'm using X bar, the sample statistic, to guess at, to estimate my population parameter. In general, we talk about this as an estimator. Any sample statistic that we use to estimate a population parameter is an estimator. And the estimate is the value of our estimator. Now, that also means I could be off. right? This is an estimate. Estimates are not perfect. So I could get some error here. And the sampling error is the difference between those two. So things like using X bar to estimate mu, like using S to estimate sigma, standard deviation to estimate population deviation. Using the number of times something happens in my experiment to estimate the chance of it happening. P to estimate pi. This one came up in our binomial, right? The top number of chance of our success versus our failure. Estimation draws conclusions from our samples. If we're drawing a conclusion, that's an inference. So frequently you'll hear this referred to as inferential statistics, as opposed to the descriptive statistics we had earlier. So descriptive statistics describe this pile of information we already had. Inferential statistics attempts to draw a conclusion from the data we have about a larger group. And the process of estimating is usually referred to that way, inferential statistics. Questions? There's quite a bit of vocabulary and theory here at the beginning. We'll do a bunch of practical examples over the next few classes. When I do a sample, one of the problems I end up with is bias. Now, bias is, there's a formula here. It's the expected value of my estimator minus the true value. So notice that this is different than the sampling error. Sampling error says, this is what I got from my sample. How far off is it from the actual value? Bias says, this is what I expect to get as a sample. How far off is it from the actual value? I would really like that to be 0. I would like the expected behavior to be as close to the true behavior as possible. If the bias is 0, then we have an unbiased estimator. It's not going to overestimate nor underestimate any more often one way over the other. You hear the phrase to err on the side of caution, or the same way to measure twice and cut once, to make sure of things, right? I don't want to overestimate, I don't want to underestimate. I want to be as accurate as I can. It turns out that X bar is an unbiased estimator. And P is an unbiased estimator for pi. But standard deviation is not unbiased. Standard deviation is biased. Wait a minute. There were two different standard deviation formulas. There was this one and the .S1. What was the difference? That's back in our descriptives chapter. That's in chapter 3, chapter 4. It's way back there. What was the difference between those two standard deviation formulas? Probably easier to find this in the textbook than in your notes. Probably. Back when we did the formula for the standard deviation, we took the difference between the data value and the average. We squared it. We added all that crap up. We divided by how many there were, and we got a square root. That's the one for P. And that almost always underestimates the population one. And so we do this. For the sample one, to push that up a little bit, if the bottom of my fraction is smaller, then the overall fraction is a little bit bigger. This is a truer, less biased estimator. So it depends on which thing we're trying to compute as to how we do it. Top of page 275. Whoops. Shows these formulas as estimators versus parameter, and notice there's the n minus 1 in the standard deviation as opposed to the n. Error is random. Bias is systemic. I used this example once before. There is a military shooting competition for the sniper school. Here are two target shooters. This is bias. The person whose target is on the right is shooting just as well as the person whose target is on the left. Their scope is not centered properly. They're aiming wrong. And every shot they fire is distributed, but in the same way as the person on the left. An unbiased estimator of the center of the target, a biased estimator. On the other hand, somebody with more variation will have targets that look like this. This person is centered. This person is centered, but this one has more variation in it. Their estimator is less efficient than this one on the right. So bias is a systemic difference that doesn't change the efficiency. Efficiency allows for more spread. Again, a bad statistics joke. 3 statisticians go hunting. They see a deer. The first one aims, bang, misses 5 feet to the right. The second one aims, bang, misses 5 feet to the left. The third one goes, we got him, on average. Even if I have a good estimator that's not biased, I can still have one that's more efficient, less efficient, or more efficient based on the spread. Again, our ideal estimators will have the minimum variance and be as unbiased as possible. In statistical language, that's MVUE. Minimum variance unbiased estimator. I would also like my estimator to be consistent. If I take a larger sample, I want it to get closer to the right answer. So my variance should get smaller as my sample size grows. It turns out average and proportion, X bar and P, satisfy all of these conditions. Standard deviation doesn't, which is why we had to deal with the difference between population and sample, the n versus the n minus 1, but all three of those are consistent, even if standard deviation is slightly biased. And that means that 99.99% of the time, those are the statistics we're going to calculate. Average, proportion, and standard deviation. And then we're going to use those things to help us out. So if I am using one of my unbiased estimators or one of my consistent estimators, I want to know what the PDF is for my estimator so that I can figure out how far off my estimate is. The sampling error of my estimator is based on the standard deviation of the parameter. So we're going to call the sampling error, the standard error, of the mean. Because we're dealing with X bar and mu. Standard error of the mean, sigma x. Wait a minute. It used to just be sigma, right? What's the x? Actually, that should be an x bar because we're dealing with a mean, right? So this is a standard error of a mean. That's why it's an x bar in there. This is given by the standard deviation for the variable divided by the square root of the size of the sample. Wait a minute, n is the sample size. What does that mean? Well, why is there an n there? What was our definition of consistent? which means if as I get my sample bigger and bigger and bigger, that means n is going to get bigger. And if n gets bigger, the bottom of my fraction is getting bigger. What happens if the bottom of my fraction gets bigger? The whole number gets smaller. Bigger my sample size, the smaller the error. Aha. So I can standardize my error by taking the sample size into account. There's an example in the text about salon facial prices. I didn't make this up. I read it out of the book. Otherwise, I wouldn't use this one. I haven't done a facial in 40 years. So let's do this one. Facials have an average cost of $80 and a standard deviation of $10. I go up to the salon and I ask them for today's facials. And they tell me 20 people got facials today. What's the standard error? It's not a cheap salon. I need you to calculate a number for me. Yes. I take the standard deviation I was given and divide it by the square root of the sample size. And that turns out to be 2.24. The units for this is still dollars. Okay, wait a minute. If I were to take a larger sample, say 40 instead of 20, what would happen to my standard error? Get smaller still, right? I had a normal population. I gave you a mean and a standard deviation. And then I took a sample from it, and the range got smaller, which means if you take the average of those 20, it'll be closer to 40 than closer to 80 than some of those individual payments would have been, right? My sample narrows how far off I am. Notice that the mean is the same between both of those two pictures. But the one on the right is smaller in standard deviation. If I have a PDF for my population that is normally distributed, that's what N means, normal, then the sample mean has a PDF that is also normal with the same mean, but a smaller standard deviation. Now, this observation that sampling narrowed my standard deviation gave rise to a very big question. What if this isn't a normal distribution? And the result, something called the central limit theorem. If a random sample is drawn from a population with mean mu and standard deviation sigma, I don't care if that's a uniform or a normal or an exponential or a triangular or any other of the PDF functions we didn't talk about. I don't care what that PDF looks like. Then the PDF for the sample mean approaches the normal distribution with mean mu and sigma over root n as its standard deviation as n increases. No matter what your original population PDF looks like, sampling results in a normal distribution. Now, I must tell you, the first time I heard this result, I flipped my lid. Said, no way. It doesn't matter what shape the PDF is. The sample is normal every time. I didn't believe it. And up until recently, I didn't have a good convincing argument as to why this would be true. Because to actually prove this result, and that's the problem with math people, is they don't just trust you, is they want to know why do you think that. There's a rigorous argument that explains why this is always true. It's about 8 pages of dense mathematics and calculus. I don't want to deal with it. Grant Sanderson, who goes on YouTube by the name 3 Blue 1 Brown, did an amazing video explaining the central limit theorem. It is in our web links section on Canvas. It isn't. It will be by the end of today. I think I already put it there. It is absolutely stunning. But what this tells me is that I need to know the right sample size to get a normal distribution. And the rule of thumb is that as long as you have n bigger than 30, you're good to go. That's not always 100% true, but it's a good rule of thumb. I will talk about the exceptions on this a little bit later, but it turns out that even small samples can give us normal distributions, but more often, as we increase our sample size, we see things that look more and more and more normal. Here's two different distributions, a uniform distribution and a very skewed distribution. Here's a sample size of 1, a sample of 2, a sample of 4, and then I'm making a histogram of how often I get a certain average. The average overall gets closer and closer to the average of this distribution. Same thing here. If I am looking at a normal sampling distribution, then I can use z-scores. And I can use our table. And I can use our normal distribution from chapter 7 to figure out things about my samples. Like what? I need you to go back in the textbook to that chart we were talking about on Wednesday, where I said, hey, we can find the middle 90% or the middle 50%, and there were z-scores that went with those. So grab your book and find for me the z-score that went with the middle 95%. The middle 95%. Page 245, the middle 95% goes with a z-score of 1.96. Okay, remember that 1.96. Because what that tells me is that I should be able to give a range and say, oh, if I know where my sample average is, the true average should be in this interval. And I'm 95% certain. How do I figure out that interval? That's where I get to use this z-score. That is what we will do on Monday. Your homework is due Monday. There will be an important announcement about the Wednesday's exam on Monday, so be here and be paying attention. I will see you all then.